Hello, I'm your TA Balaji and I will be discussing the solutions for assignment 11 now. Question 1. A combinational circuit for y is equal to a plus b is made of a NOR2 gate driving an inverter. If the TPD of NOR2 and inverter are 9 nanoseconds and 3 nanoseconds respectively, the throughput of the system can be improved from dash inputs every dash nanoseconds to dash inputs every dash nanoseconds through pipelining. So let's just look at this circuit y is equal to a plus b, right? So the circuit has a NOR2 gate followed by an inverter. Now let's say we pipeline it in the middle here. So how will the circuit look like right after pipelining? So you will have a flip-flop here, a flop system here, a flop here, all of these connected using a single clock, right? So what can you say? You can pipeline it with a clock period of 9 nanoseconds, right? So initially the total delay of the system would be initially without pipelining. Let's say you just had these two, this and these two flops. So the total time period initially was equal to 12 uh, was equal to 12 nanoseconds. Now after pipelining, now you can reduce the time period to 9 nanoseconds with one input being fed, which is right. Also you could also double. Basically you could have 18 uh, you could also have within 18 nanoseconds you could also process two inputs, so hence the throughput increases. So option A and D are both right. Okay. Question 2 to 10. For the sequential circuit below, answer the following questions 2 to 10. The circuit shown in figure 1 is, so this is a positive edge triggered flip flop, as it is a negative latch followed by a positive latch. So hence it's a positive edge triggered flip flop. Right? Question 3. If one removes T2, I3 and I4 from the sequential element in figure 1, the remaining circuit with the D and output QM is. So basically if you remove this portion of the circuit, which is this portion of the circuit, the remaining portion of the circuit is just this. And the remaining portion is a negative latch, right? Moving on to question 4. Which of the following data will reach QM? So since you can see that since you can see that to reach QM, all that you need to do is to allow data during the phase where clock is equal to 0. So when you look at all of the signals, D1 is when clock is equal to 0, D2 has a portion where clock equal to 0, D3 and D4, all of them have a portion where clock equal to 0, so hence all four are right answers. Which of the following data will reach Q? So what will reach Q is when only in clock equal to 0. So it should happen exactly during the transition, right? So if you look at the transition time, which is this portion, so D2 has it, but however if you look at D1, it happens only during the phase where clock is equal to 0. So D1 doesn't reach uh, doesn't happen during the transition edge. However, D2, D3 and D4, all of them happen during the transition edge. Hence the right answers are D2, D3 and D4. The circuitry driving input D can be of any strength and this sequential element will work properly for it. It is false since it has to overpower T1 and I2. Basically it has to overpower this path from here to here. So basically, the I2 will be a transistor having one PMOS pulling it up to VDD and one NMOS pulling it down to ground. So the input which is driving D needs to overpower either this path or either this path. So it needs to overpower I2 at least, and hence uh, false. The circuit will work for any strength of I1, I2, I3, I4. Now this is definitely false, as I1 needs to be greater than I4. Why is that so? Because as you could see in the previous case, you needed this path to overpower. So the input, the circuit is driving, let's say D, needs to overpower this path. Similarly, when you look at this path, so I1 needs to overpower I4 in order to uh, change the value of this node, right? So there definitely exists the condition, and hence the answer is false. In the circuit of question 3, with input D and QM, noise in the output can disturb the internal state. So again, so let's look at this figure. This is the circuit of question 3. Now any noise in the output as shown in green, right? So this is noise from the output. It can just traverse through I2 and go this way and disturb QM and also this value, right? So can and hence it disturbs the internal state of the flop of the latch. Sorry. In the circuit of question 3, if one gave QM as the input to an inverter and took the inverter output QM bar as the circuit output, then the noise of the circuit can still disturb the internal state. So that's not true. As you can see here, this is what is being suggested in the question. So this is the output, right? QM bar. So now if you look at any noise that does not traverse that does not go through as in the previous case. So it is just at the output of an inverter and just remains there. It does not go through and affect any of this path. So it does not affect that path, and hence the answer is false. Okay. So question 10. In the circuit in question 3, with input D and output QM, writing data happens by. So writing data always happens through overpowering the feedback. Let's say when D is equal to 0, you can look at this purple, this pink path. Sorry. So if you look at this pink path, it needs to overpower the PMOS. So when you are writing, uh, given that a 1 is previously present in this at this node. Now again consider the other case where a 0 is present at this node, then the output should whatever that is driving D needs to overpower this path, which is the pull down NMOS. Overpowering the feedback loop occurs when clock equal to 0. Exactly, that's because even for this path to even activate, clock should be equal to 0. Right? Okay. Question 11. Race condition due to clock overlap on the sampling edge can be overcome by imposing a hold time constraint alone. So yes, that is definitely true because race condition occurs in a latch-based system where there are phi 1 and phi 2, and let's say phi 1 and phi 2 have an amount of T overlap. So, what does T overlap mean? All that it means is when latch one. So, how does a flip flop work? Uh, when let's say latch one is transparent, latch two is opaque. This is the first phase, right? So after this phase, latch one becomes opaque and latch two becomes transparent. So at so for a and this is for a positive edge triggered flip flop, right? So or positive edge triggered system, right? So wherein you have a flop here which is controlled by phi 1 and there is a flop here, that is a latch, sorry, a latch here that's controlled by phi 1 and latch here controlled by phi 2. Now when you look at it, the data, right? So if let's say the data is able to the data is given here to this latch. Now what happens if let's say phi 1 and phi 2 has an overlap here? When there is an overlap, all that will happen is uh, both of these latches L1 and L2 are turned on during this phase, and the data that is here just rushes or just races through and goes to the output. So uh, all that we can do to control this is to impose a hold time constraint, and the race condition can be avoided. So this is called race through. So questions 12 to 16. Uh, what is the type of sequential element? So question 12. What is the type of sequential element shown in figure 3? So the type of sequential element shown in figure 3 is a negative latch. Why so? Because when clock is equal to 0, that's when the data can flow. Basically when clock is equal to 0, this TG is enabled and data flows all the way this way. This is how data flow happens, right? And again this path helps to retain the when clock is equal to 1, right? When clock is equal to 1, this helps to retain the data, and when clock is equal to 0, this helps to move the data forward, right? Which is the path as shown in red. So this is definitely a negative latch. What is TDQ of the sequential element shown in figure 3? So the TDQ here is TTG1 plus TI1 plus TI3, which is basically this one plus TI1, as in it goes this way, TI1 and TI3. 1 plus 2 plus 1, which is 4 nanoseconds. Now what is the T setup of the sequential element? So always for setup time we need the feedback path to have settled. So that's exactly what we are looking for here. So which is nothing but TG1 and TI1, and due to this the feedback path TI2. So all of this must settle. Basically we are looking at this node, and we are seeing with, so let's just clear this up, and all that we are looking is that given this path, right, given this path, so this has to settle. Basically we're looking at this node. So this node has two paths, one from this side, one from this side. So both of these should not collide, or rather both of these, if the value due to this path settles before uh, anything changes here, that is exactly what we are looking for, which is the setup time. So TTG, no wait, yeah, TTG1 plus TI1 plus TI2, which is 1 plus 2 plus 2, 4, 5 nanoseconds. For the D flip-flop constructed using the element in figure 3, answer questions 15 to 17. So for a D flip-flop constructed using this, right, answer the following. Clock overlap is not an issue. So always clock overlap will be an issue when two latches are present And as you can see, the race through is the condition that happens when two latches are present, and therefore clock overlap is definitely uh, an issue. So false is the right answer. Driver strength is not an issue. So this is true as feedback is broken. So you can look at this when data is equal to when clock is equal to 0. When this latch is transparent, the data just directly goes here and goes to your output. You don't need to overpower the feedback loop, as the feedback loop here is broken. As clock equal to 0, this NMOS is off, and clock equal to, I mean, this clock bar which is 1, and this PMOS is again off. So this path is broken. So there's just one path from here to the output, and therefore true is the right answer. What is the T clock to Q? So T clock to Q is nothing but TG1 plus TI1 plus TI3, which is nothing but this plus this plus this. From the instant clock goes to Q. So basically it's clock to Q. Now when you look at what is T hold of the circuit, uh, so the transmission gate switches off. So when you look at what is T hold of the circuit, we need to come back to the assumption where it is stated that you may assume instantaneous clock edges and the transmission gates open circuit as soon as this clocks deactivate, right? So when you look at this, uh, it says the transmission gate instantaneously switches off, so no time is needed for transparent to opaque conversion. So hence the T hold is 0, right?